Thanks. Well, everybody, welcome. Good that there are people who want to see my presentation. This is good to know. My presentation tonight will be on the division of silicate minerals and actually the groups in which they are divided into. Since I started collecting minerals at 12, I was always intrigued by what kind of minerals there were in the rocks that I picked up during my holidays with my parents in Italy or with my grandparents in Germany. Later, a few years later, I learned that the majority of them belong to a group called silicate minerals, which happens to be the largest group of minerals in the world. I had no understanding about them, and I don't know, well, I knew nothing about how they were made up. So I thought it was time to look into that, and then I understood a whole lot more. I hope I can make you see that the silicate minerals are a great group to collect. Well, by no means does this presentation pretend to be complete, but I can see it just as a start. First of all, what's a silicate mineral? Well, silicate minerals are rock-forming minerals that are made up of silicate groups. They are the largest group of minerals and make up approximately 90% of the Earth's crust. So that's quite a lot. Approximately 29% of all known minerals and 40% of the most common ones are silicates. So about 1,700, pending publication of some others. And a silicate mineral is generally an ionic compound whose anions consist predominantly of silicon and oxygen atoms. And the fundamental unit in all silicate structures is the silicon-oxygen tetrahedron, composed of a central silicon cation bounded by 4 oxygen atoms that are located at the corners of a regular tetrahedron. Like I said, the division of silicate minerals is into groups. There are 6 major silicate groups, and they're all based on the structure of positioning of the silicon tetrahedras. So there are nesosilicates, which are isolated silicon tetrahedra, sorosilicates, which are double tetrahedra, cyclosilicates, which are ring tetrahedra who form rings, single or double, inosilicates, which form single chains or double chains, the phyllosilicates, which form sheets, and the tectosilicates, which are the most comprehensive ones, which form a 3D framework and are commercially highly valuable. The nesosilicates, I start with the simple ones. There are approximately 247 of them, and it was called orthosilicates in the beginning. They left the name orthosilicates, and now they call it nesosilicates. And the name Neso comes from the Greek word Nesos, which means island. You can understand why, because they are all tetrahedra, isolated tetrahedra islands, which are connected only by interstitial cations. The nesosilicates form groups, like I said, and they include, amongst others, the following: the phenakite group, olivine group, garnet group, zircon group, the Al2SaO5 group, the humite subgroup, and of course many others. The phenakite group. The phenakite group consists of only 3 minerals. If you notice, there are 2 colors in my naming from the minerals. The black ones are in the presentation, and the asterisk behind the name is that I have it in my collection. So the first one, phenakite. Phenakite is a beryllium silicate, and these are colorless crystals or matrix from the Steepleman mine from Erongo, Namibia. On the right-hand side, you see a crystal drawing, which mostly all of them come from the mineralienatlas.de. And the square in the lower right-hand corner gives you the commonality of the mineral. Green means common. The crystal system in which it crystallizes, and the Mohs hardness. Next one of the group is willemite. Willemite is a zinc silicate, and these are actually a whole bunch of colorless willemite crystals on very little matrix from Cedar Talisman mine in Utah, in America, the United States. The next group is the olivine group, and specifically the phosphate phyolite series. The olivine group consists of 9 minerals with the chemical formula M2SeO4, where M can be calcium, iron, manganese, nickel, or magnesium, or a combination of both of them. In this presentation, I only have 3. The first one is phyolite, which presents as elongated brown crystals with termination from the Nickel Sattel in the Eifel, in Rheinland-Pfalz in Germany. The width of the picture is stated above the picture, so it's only 4 millimeters. This is really a micro. Phosphorite, which is actually the magnesium silicate of the series. It's also from the same locality, the Nickel Sattel. And they are actually identical in crystal structure and hardness, but they have a different chemical makeup. Monticellite, sorry, is a calcium magnesium silicate, which forms platy distorted crystals. Unfortunately, this one comes from the Kofdor Selesny mine, from the Kofdor Massif in Kola. I didn't do a presentation on that one yet. I did Kibini and Lovazero. There's a third one, which is equally interesting. Then a group that everybody knows, the garnet group, consists of 14 minerals with the chemical formula, blah, blah. I don't bother you with that. And I only show you the most common ones, the ones I have in my collection. This is actually not a micro. It's 35 by 30 by 32 millimeters, but it's a nice dodecahedron from Dar-e-Pech in Kunar, Afghanistan. This also is, again, not a micro. It's 25 by 20 by 25 millimeters, an andradite dodecahedron with smaller ones attached to it, from Sibindi in Mali. The next garnet is the Grosseler family, and also showing dodecahedrons, this time yellow brownish ones. And they come from Lago della Sella in Trentino Alto Adige in Italy. All garnets are, by the way, isometric. They crystallize in the isometric system. This is a pyrope crystal, a single pyrope crystal, and it's rather distorted. It's not complete. And when I got this from a dealer, it says only Spain. It was labeled Spain. I find that highly doubtful. So I tried to look up the most possible location or locality it can come from. And I came up with a Czech Republic locality, but I'm not sure about that one. The spessartine garnet series, they form nice trapezohedral crystals. This one is from the Wuhan spessartine mine in Fujian in China. Very nice crystals, very orange. And the piece, it's on autoclaves, and it's virtually littered on with the crystals. The calcium chrome silicate garnet, which is uvarovite. It has a modified dodecahedron shape, and it comes from the Vuonos mine in Outokumpu in Finland. The next group is the zircon group, still belonging to the Niso silicates. And they have a formula with MSeO4, where M can be either uranium, zirconium, thorium, hafnium, or cerium. I do have 3 of those, but I only show you 2. The first one is thorite. And the thorite is actually the dark green stuff on the right-hand side. And the crystal on the left is actually zircon from the Bassano Romano in Lazio, Italy. These are very nice zircon crystals on the matrix from the Eifel and the Glaserfelder. They are actually very well terminated, and I don't know what the other dark material is. I'll have to look into that. The Al2SCO5 group. Well, that's actually not a group, but it's a set of minerals which are polymorphs. And it's andalusite, kyanite, and sillimanite. And in this case, I have a variety of andalusite. It's called chiastolite. And they form brown-yellow crystals with a cross and a dark center made up of graphite from La Chapelle du Mur in Bretagne, France. Kyanite, this is an elongated, very light blue crystal with striations from the Barra do Salinas in Minas Gerais, Brazil. You see here that the field of view is 8 millimeters. It's slightly larger. Sillimanite is actually a colorless crystals over here. They are not very well photographed, I see now. Sorry for that. But it also comes from the Eifel, the Wingersberg, near Mendig in Germany. The Humite subgroup. Well, there are 6 minerals in this group. And they have, again, a formula with an N for the formula, which stands for times 1, 2, 3, or 4. And I only will show you 3 different ones. First of all, the chondrodite. It's orangey crystals, slightly rounded, with minor phlogopite in calcite matrix from the Mountjoberg lime quarry in Gävleborg, Sweden. Clear humite, which are yellow crystals with some green chloride minerals in quartz matrix from the Lakeview mine in California. And norbergite, which is a deformed orange yellow crystal in calcite matrix from the Limberg quarry in Finland. So you see all my samples, specimens are from all over the world, and that's what I like. To show you some other niche silicates like dumortierite, staurolite, titanite, and topaz, each in their own groups. Dumortierite is normally a blocky crystal, but you can also see very elongated blue crystals. This comes from Madagascar, Tsiambenana. And the other name I'm not even going to try to pronounce. So I'll probably say it wrong. Here's a nice staurolite, the penetration twin from the Apex mine in Chihuahua, Mexico. This again is very large. It's 12 by 14 by 12 millimeters. And a green, doubly terminated titanite green crystal from the Habach case in Bromberg am Mühlkogel in Salzburg, Austria. Should say something to Gerhard. And of course, topaz, colorless, elongated crystals with end faces from the Cove, Topaz Mountain, Utah. That was the nesosilicates. Now we go to the next one, which are the sorosilicates. The name soro comes from the Greek word soros, which means heap or mount. They have isolated pyrosilicate anions consisting of double tetrahedra with a shared oxygen vertex. So they get a silicon to oxygen ratio of 2 to 7. Well, some minerals and groups: the hemimorphite, the axonite group, the epidote group, and the Vesuvianite group. To start with the hemimorphite, these are groups of radial-shaped sprays of pointy crystals, white crystals, from Corte San Valentin in Murcia, Spain. These are pretty well distinct colorless axonite ferrous crystals from Puiva Mountain in Tyumen Oblast in Russia, which is in the eastern side of Russia. The epidote group, there are 11 minerals in that, and I only have 3 of them, correction, 4. First of all, the clinozoisite. And this also comes from Austria, in Steinbruch-Irsa in Canton. They are elongated prismatic crystals, and there are also some white rounded prehnite crystals and some green chloride mineral on the crystals. Epidote. Well, you can see the striations in this one. And this is from Fuchsbau in Bayern, in Germany. But it also shows the end faces on one side, so that's good. I have other epidote specimens. This one comes from the Altuuri alpine clefts, which do not show the striation, but, well, sharply defined end faces in Pakistan. And the third epidote specimen is from Sonkar in Salzburg, Austria, a large group of well-terminated epidote crystals. And Piemontite from the Krembruch and Bayern, which is dark red-brown. It doesn't look that way on the picture, but through the microscope, the red-brown color is shown. Then we get the Vesuvianite group. Again, I only have 2 of those, but pretty nice ones. First of all, the Vesuvianite from the South Africa, which are dark brown crystals. And the blocky crystals from the type locality Montesoma in Italy. And there are some colorless wollastonite crystals attached to the matrix. And willowiite is also from the type locality, the Vilju River Basin in the Sakha Republic in Russia. And it shows, well, actually the same crystal form over here as in the picture. So that's cool. You skip to the next group of silicate minerals, which are the cyclosilicates. And the cyclo is because we made it an English word, but it comes from the Greek word kykelos, which means circle. And they are ring silicates and have 3 or more tetrahedra linked in a ring. And then a silicon to oxygen ratio 1:3 in single rings, and a ratio of 2:5 in double rings. Some members of the groups, the 3-membered ring, single ring, is the benitoite. We got the beryl and tourmaline group, the 6-member ring, and the 9-member ring is the eudialyte, and we got a 6-member double ring. It's called isolite. Beautiful blue benitoite crystal from the Junilla mine in California. Some pretty hexagonal shaped columns from the Tubusis farm in Orongo in Namibia. This is aquamarine, very light blue. Other tourmaline species, of course, are albaite. Albaite can either be rubellite, verdilite, and there are some more varieties. This is the verdilite, it's green, and it comes from Jerry's claim, also from Orongo in Namibia. And the black tourmaline, or schorl, and this one comes from the Torstein Larvikite quarry in Larvik, Norway. The eudialyte group, and in this case the eudialyte mineral itself, is pink-red, and it is here in matrix, probably albite matrix from the Pouce-Red quarry in Mont-Saint-Hilaire in Canada. And isolite. Well, isolite, this is not my picture, I have to admit. I got it from the dealer I got the specimen from. And this is Joy Desor. And it's actually a very good picture, and it resembles the crystal drawing very well. It's very rare, and it comes from the Eifel Steinbruch Kaspar in Germany. Next group, the inosilicates. Well, the name ino comes from the Greek inos, which means fiber, and they are chain silicates of tetrahedra with either a ratio of 1 to 3 in single chains or a ratio of 4 to 11 in double chains. These are the most common minerals that occur on this earth, like the pyroxene group, the wollastonite group, and the amphibole group. The pyroxene group consists of a large number of minerals. It's actually in the triangle on the right. You can see the lines from here. Those are the pyroxenes, and they are divided into two: the clinopyroxenes and the orthopyroxenes. And we start them off with azurine. The azurine is a very common mineral. Blue stands for widely spread. And this is actually a slightly damaged tapered crystal from Mount Melosa in Malawi. Azurine augite, and actually these are the ones it is about. It's again from the Eifel, from the Glacier Valley in Germany. And they produce blocky crystals. The next one is a favorite of mine. It's an augite crystal, also from the Eifel, from the Wingetsberg. And although you can not really see the end faces, you can see the side faces really good. It's highly lustrous, and there are some minor titanite crystals in the specimen. Diopside, well, actually this is a damaged crystal, but it is still attached to the matrix. And it also comes from the Monte Somma in Italy. And this diopside comes from Tasmania, Australia, from the Kara mines. And it's more blocky. And also it resembles the crystal drawing perfectly. The next pyroxene is enstatite. These are elongated light brown crystals on sanity matrix from Roc de Coulombe in France. And there are elongated crystals, there are some blocky crystals here, and some other pyroxenes, which I don't know which they are. I'll have to look into that. The ferrocyanide crystals comes from also the Eifel in Daxbusch, in Rheinland-Pfalz in Germany, and they are small, because it says here the field of view is 4 millimeters. The crystal is probably under a millimeter. Pigeonite is another pyroxene. This one comes from the Old Goose Creek quarry in Virginia. This one is slightly tarnished by some probably elements which I don't know. And there is another one to the right of it, which does not resemble the crystal drawing. So I only circled this one. The wollastonite group is actually not an IMA recognized group. IMA stands for the International Mineralogical Association. But the chemical formula is similar and consists of 13 minerals. I shall only show you the three I mentioned here: pectolite, serundite, and wollastonite. This is a very colorless and perfect terminated pectolite crystal on biotite matrix from the Poudret quarry in Mont-Saint-Hilaire in Canada. These are highly elongated orange-brown crystals in an Usingite matrix from the Jubilanaya pegmatite in Lovosero in Russia. And the last one from the group is wollastonite, actually para-wollastonite, and it is actually intergrown yellow crystals in the whole piece. So, but you can still see some shapes of the crystals from the 4955 mine in Washington. We change to the amphibole subgroup. Also a very large number of minerals, and they can be divided into the W cation, oxygen dominant, or hydroxyl fluorine or chloride dominant. They are very a lot of them are all elongated prismatic crystals, like the actinomite. This one comes from Food Sauerkar in Schwarzwald in Austria. And there are actually a bunch of loose crystals. And actually the determination is not that good. This is arfetronite from Mount Melosa, Malawi. I already had shown you a mineral from Malawi. And this is actually a number of parallel growing prismatic arfetronite crystals on an autoclave matrix. This is actually a spray of radial shaped group of cummingtonite crystals. They're brown. They come from New Zealand, the Jacobs River. This one is particularly nice. It's a single black slim prismatic crystal on tritiumite with light green phyllite from the Henderson's quarry in New Zealand, and it's called ferroedenite. This is a funny story. I just exchanged this one with Henk Smeets 3 weeks ago now, when we had our Micromount trade day in Eemnes, the Netherlands. And he found that on his last trip to the Azores in the pumice quarry, Ribeira Grande, the ferrocataphorite. The next amphibole is ferro hornblende. And these are actually etched out of serpentine matrix. And they look really like the crystal drawing from Algarrobico in Almeria, Spain. Velcophane, another amphibole. It's actually gray, and there are always parallel growing crystals from France. This time it's the Mine Le Clossy. And then we got grunerite. They are not all that aesthetic to see, but they are very, very nice in crystal shapes. It's dark green prismatic crystals on matrix from Flowerdale Mains in Scotland, Gavelog. This one is an orange one, orange prismatic crystals on matrix, the Gershuptite, also from the Eifel, from the Rotenberg. The light orange ones is a different mineral. I can't remember which one. But the dark orange ones are Gershuptite. And also crystal forms can be a bit fibrous, like this blue-gray magnesio-rebecite from the Caroline mine in Cochabamba, Bolivia. Then we go on to Pargasite from the type locality green crystals, very dark green crystals in calcite matrix from the Limberg quarry in Finland. And white elongated groups of tremolite crystals from Toel del Mason in Trentino Alto de Adige in Italy. Next group, the phyllosilicates. The name phyllo comes from the Greek word phylon, which means leaf, and they are sheet silicates of tetrahedra with a ratio of 2 to 5. All phyllosilicates are hydrated with either water or hydroxyl. Specimens can come from the serpentine subgroup, the chloride group, or the mica group. They are easily split because they are sheets, made up of sheets. Serpentine subgroup, well, you got a whole lot of minerals there. And the first one is amosite. Amosite is fun to collect because only of its color is purple. And if you're lucky, you can get a crystal which is really nicely crystallized. This is from the Saranovsky mine in the Permkraj in Russia. Well, this one I wasn't sure if I put in, but it's actually an interground tabular crystal, yellow-green, from antigorite, from an unnamed serpentine quarry in Argentina. And this is lizardite. It's difficult to see in the picture, I realize now, but they are thin, platy, pale green crystals in dolomite matrix from the Otamo dolomite quarry in Finland. The chloride group. Again, a lot of text, but you can read that on your own if it's on YouTube. First of all, the cleaner chlor is the name giver of the group. Nice single platy crystal, rather large, 11 by 11 by 2 millimeters, from the Saut de Lup, an Auvergne going out in France. This is also a nice one. This is cookieite, green spherules, consisting of tightly arranged crystals from the Stand on Your Head #1 mine in Saline County, Arkansas, United States. The mica group. Well, mica is a common name, and it stands for a large group of sheet silicates that can be parted into flexible orbital sheets. It includes the true micas like muscovite, paragonite, and ephesite, and the brittle micas like margarite and clintonite. They are all called just the mica family. There are quite a few minerals which you don't expect to be a member of the mica family, but this is one. It's called annite, and it also comes from the Eifel. It's actually two crystals sitting on top of each other, or laying on top of each other. You're looking on the side, and the first one on the left is actually very, very broad. The second one is more like the picture of the crystal drawing. This one is a rare one. It's called Chernikite, from the Karto mine in Kazakhstan, and it's also a platy crystal with nice green ones. Ephesite forms crystals which are not fully developed. This one comes from the Gloucester mine and the Northern Cape province of South Africa. A pink crystal aggregate. There's no matrix on this one. Of course, muscovite. This comes from the Ray Mica mine in North Carolina. But I also purchased one on the show last Saturday, which is a rather nice aggregate of muscovite crystals from Brazil. The phlogopite. This is also a from the mica family, and this one comes from Mina Nuestra Señora del Carmen from Jumilla in Murcia, Spain. Light brown platy crystals on calcite matrix. Well, the last group of silicate minerals, the tectosilicates. The name tecto comes from the Latin word tectos, which means a roof. It is actually a three-dimensional framework of silicate tetrahedra with SO2 in a 1:2 ratio, and all tectosilicates are aluminosilicates. In this group, you find the feldspars, the feldspathoids, and the zeolites. Very interesting group. The feldspar group, well, it is by far the most common mineral group found on the surface of the Earth. And it consists of a large number of minerals that can be divided into two major subgroups. The alkali feldspar, ranging from sanidine to high temperature albite, and the plagioclase feldspar, ranging from albite to the anorthite series. First of all, albite. This is actually a double terminated crystal, colorless crystal from Steinburg-Osling in Saxon, Germany. This is an anorthite crystal, a colorless anorthite crystal from Montesoma, type locality in Italy. This is the variety hyalophane for microcline. It's a thin, platy, colorless crystal from the Miniera di Monte Arsicchio, also the Monte Arsicchio mine, from Stazzema, Toscana, Italy. And of course, autoclase, which is a Carswell twinned crystal in which the twinning axis is the Z-axis. The operation is rotation of 180 degrees, and the contact surface is parallel to the side pinacoite. This is quite common in alkali feldspars. I have a larger one, which is approximately 5 centimeters in height. Then we got Sanidine, also from the Eiffel, colorless crystals on matrix. Then we go on to the feldspathoids, which are not really a group, but are a family of rock-forming minerals consisting of aluminosilicates, of sodium, potassium, and calcium, and having too little silicium to form feldspars. All have seen most of those, like the Howie. Unfortunately, my crystal broke when splitting the rock. It actually separated, but stayed on the matrix, so that's good. I have a few more, but they are not that well crystallized. This is also from the Eiffel in the Dellen in Germany. This is a colorless trapezohedral crystal of lucite from the Eiffel in the Grauwei. There are a whole bunch of other. I calculated that there were at least 10 other minerals in this picture, so very difficult to distinguish them. Very nice barrel-shaped colorless nepheline crystals, also from the Grauwei in the Eiffel. And some small white rounded modified dodecahedron sodalite crystals on matrix. The sodalite in the Eiffel is almost always rounded due to temperatures when it emerges from the ejecta. Well, a very interesting group, the zeolite group. The zeolite group is a large group of framework aluminosilicates which are built of cornel-linked tetrahedra and contain exchangeable cations. That makes them interesting. There are a lot of zeolites, around 100, and a lot of them have important technical applications. The IMA gives as a definition of zeolites: a zeolite mineral is a crystalline substance with a structure characterized by a framework of linked tetrahedra, each consisting of 4 oxygen atoms surrounding a cation. This framework contains open cavities in the form of channels and cages, and these are usually occupied by H2O molecules and extra framework cations that are commonly exchangeable. The channels are large enough to allow the passage of gas species, and in the hydrated phases, dehydration occurs at temperatures mostly below 400 degrees Celsius and is largely reversible. The framework may be interrupted by hydroxy or fluorine groups. Only these groups occupy a tetrahedron apex that is not shared with adjacent tetrahedra. Well, the commercial uses of the zeolites are, well, it's widely used as a catalyst and sorbents. For membranes to separate molecules, in ion exchange beds for water purification, as water softeners in laundry detergent. It is used in nuclear reprocessing methods, gas separation and storage, thermochemically storing solar heat, and not the least, it is used as cat litter. The first one of the zeolites is anancine. This is a trapezohedral crystal, but it crystallizes in the triclinic system. So it's actually a pseudo-cubic crystal. And it comes from the Poudret quarry, Mont-Saint-Hilaire. Brewsterite strontium from the Belfgrove quarry, which is the type locality for the strontium, the Brewsterite strontium. Those are elongated, flattened end faces crystals. Chamosite cubes from Oliver's Road in Tasmania, together with spherical Phillipsite subgroup aggregates. Those are the darker ones here.
They're Thompsonite, actually.
They're Thompsonite. Okay, that's good. Good to know. Phenoptilolite. It says here calcium. I'm not sure about that. There are light green, tablet-shaped crystals on the matrix from Will Hazard in Cornwall, United Kingdom. Calcite. Calcite forms spherical aggregates from tightly arranged crystals in a cavity in basalt, in this case, from Orskell Bay, Scotland. Erionite crystals, prismatic barrel-shaped crystals, always together with ophertite and the Bonacker quarry in Darmstadt, Germany. Feuersite, calcium, it can also be sodium, I don't know. But they have, from this locality, Steinbrück am Limberg, in Baden-Württemberg in Germany, they have also cracked surfaces. It looks like it has been blown apart and then put together again. It's very funny. Ferrite magnesium from the type locality Pinas Lake in Canada, British Columbia. And the spherical iron-stained aggregates consisting of tightly packed crystals. Well, they are visible here with the naked eye in this picture. A very nice group of tabular hexagonal crystals of camelinite. I acquired this one recently, and it's also from the Poudret quarry in Mont-Saint-Hilaire in Canada. This is gonadite, also from the Poudret quarry, but they are actually formed as blocky crystals, white. Nice harmotone crystals, colorless, prismatic, with end faces. Over here. I can't pronounce it, that name, but it's from Wales.
Klein Minogue.
Klein Minogue?
Klein Minogue.
Yeah. I'll leave that to you, Martin. Also, the next one is Eulandite. Eulandite from India, the Nashi quarry. Tapered crystals, light green. Lontite is the next zeolite. Also elongated blocky crystals from the Pluton de la Cabrera in Madrid, Spain. Very nice white platy Levine crystals. If it's Levine C, I cannot say for sure. But that's how I got it in my database. From the Beach Creek quarry, Mount Vernon, Grand County, Oregon, United States. Mordenite, shown here as radial-shaped structures of groups of acicular fine crystals from Brastis in Réunion in France. Well, it's not in France, it's in Réunion, which is an island. Blocky crystals from Natrolite. Natrolite normally is as fine as acicular crystals, but this one is rather blocky. Also from the Poudret quarry in Canada. Ophertite, which are the colorless prismatic crystals. The yellow balls are spherical calcite from Vinarice in the Czech Republic. Just like the next zeolite from the Czech Republic is polingite, which is actually a rare mineral there. And there you can see a crystal like the drawing. Philipsite, this is a rarity in the crystal form because they are actually twins. And they are twinned, not in the way you know it, but they are twinned on each other and making elongated prisms. And there are actually two in this picture. From the basalt, well, basalt means quarry, basalt quarry shrimp in Hessen in Germany. Acicular, water clear scodesite crystals. It's actually a close-up of a piece which is actually larger than the micro. It's about 5 centimeters wide and 4 centimeters high. From Chandurni in Maharashtra, India. Stilbite, it says Ca. It can be Na, but I think it is Ca. From the Giant's Causeway in Northern Ireland. Stilbite crystals on matrix. And the last zeolite is Thomsonite, which is shown here as a successive growth of tabular crystals on each other from the Punaru Valley in Tahiti, Polynesia. That was the last mineral I wanted to show you. Are there any questions?
That was excellent. Thank you.
It certainly was.
Very good. Very good.
Thank you.
A couple of my favorite
Yeah,
groups
very
of
good.
minerals in there.
Yeah, I thought you would like it, Paul.
Yeah.
I think it's a very well explained version of the silicate group.
Mm.
Yeah.
Very
I
good.
never actually gave it any thought until I just plunged into it, and then oh right, that's how it is, and it makes sense why the zeolites are commonly commercially interesting because they have exchangeable cations.
There's one major group though that was missing, and that's the clay minerals, and that's because there's no photos to show.
No, I don't have any minerals to show with decent crystal forms.
There aren't any.
No.
Yeah, ever. I've never seen a crystal of clay except under a very high-powered microscope.
Yeah,
probably a scanning electron microscope is.
But you're right. They were initially in the presentation, but then yeah, the browns and the yellows are not that interesting, I think.
I mean, some of the zeolite locations like Phillip Island, Flinders and Bandura, you do get coatings of very pretty clays on the cavities. I've seen blues and reds and greens and browns and whites, and they change color as they dehydrate as well.
Yeah.
I think one of the nicest I've ever seen was a vug was broken open at the Bandura quality, and there were buttons of orange calcite on a bed of pale blue clay. It was just spectacular.
Yeah. The contrast is great.
Yeah, and
but
then
they
it dried out and went
very
white.
quickly. So.
Yeah.
I had some specimen from Austria, Gerhard. So.
All
right.
No questions. Must have explained it really, really well.
Very well explained. Yeah, very well explained.
Well, I did have one.
Okay.
Why, do you know why Wollastonite is not a recognized group?
IMA has ways which I cannot understand because they keep changing things and names and whatever. So I'm not a member of the IMA, so I have no idea.
Yeah.
One of the things is that the groups are kind of loose because they're based on structure, but if you have these complex structures where you have sheets as well as, I mean, layers. You may have a layer that's a sheet, and then another layer that's a double sheet, and then a
Yeah.
layer that's
Correct.
contacted tetrahedra.
Yeah,
And so what group do you put that in?
Hank's late to the party.
Yep. Welcome,
And
Hank.
that's part of the problem. The more complex the structure, the harder it is to stick it in a single group.
Yeah.
Correct.
Hank,
You
sorry.
missed it, Hank.
You missed it, yes.
Sorry,
You've missed it. We've just finished.
I'm an hour late.
Yes.
Yes.
Yeah.
Oh my goodness.
But welcome anyway.
Oh,
Yeah,
Frank,
do you-
start
hey-
again, please.
Hank, yeah, do you have any
Frank,
questions
Frank,
about
Frank,
silicates?
Frank, can you do it again?
Yeah, sure. Do you have an hour?
Oops.
All right. Hank, you'll have to watch the recording.
Yeah, sure, of course.
Okay, if there's no more questions, we'll finish up. And we'll see you. Don't forget, next one is 1 week later than usual.
Yeah, it's very cozy tonight. Thank you.
All right.
Okay,
We'll see
Good
you
night.
all next month.
Yeah.
All right.
Bye-bye.
bye.
Yeah.
Thanks
Bye,
again,
Steve.
Hope you
Steve.
enjoyed it.